Ladies and gentlemen, welcome to my presentation on robust interval observer design for fractional order models with application to state-of-charge estimation of batteries. In this presentation, we will have a look at different options how to model the battery dynamics in order to forecast the state of charge, prevent excessive discharging and overcharging, to detect aging, as well as to equalize the state of charge if we have multiple battery cells that are connected in row or series. For that purpose, we can either employ low-dimensional integer-order equivalent circuit representations or fractional order models. In both cases, typically non-linearities due to state of charge and temperature dependencies of parameters as well as the open circuit voltage have to be taken into consideration. First of all, let's have a look at corresponding integer-order system representations. They are typically given by these Thevenin equivalent circuit models in which we have a series connection of resistors and several RC submodels. Here the parameters alpha, beta and gamma on the left-hand side, they can be introduced in order to describe non-directly modeled aging phenomena. What we will identify is during an experimental investigation by using impedance spectroscopy is the corresponding amplitude and phase responses. We will figure out that amplitude responses are typically not integer multiples of plus minus 20 decibels per frequency decade, and also the phase variations, they do not typically correspond to integer multiples of plus minus p-half per frequency decade. This can also be seen here in this graph here for the magnitude and the phase response. Due to that fact, typically those integer order system models, they can only serve as an approximation of the frequency response characteristics over a finite bandwidth. Corresponding information about integer order models can be found in those two references, where the latter one is the one from which I had taken the graphs of the magnitude and phase response on the previous slides. Corresponding generalizations to fractional order system models account for a generalization of the frequency response characteristics by those expressions that you can see on this slide. There, we do not have integer powers of the corresponding terms j times omega, where omega is the angular frequency, but we account for fractional order powers here, where gamma is a real valued parameter between 0 and 1 of this corresponding open interval. In such a way, we can try to approximate the amplitude and phase responses that you can see here again on the slide, where R0 and R are typically either constant parameters or state of charge dependent characteristics. The same also holds here for the open circuit voltage, and Q is a generalization of a capacitor by means of a constant phase element with a corresponding fractional power gamma, where gamma, as I already mentioned here, is taken from this open interval. Corresponding information is also cited in the list of references here on the slide, as well as in our proceedings paper. What are the typical characteristics here of fractional order linear system models which are time invariant? They can be described by those corresponding linear fractional differential equations, where A, B, C, and D describe the system matrix, the input matrix, an output and feed-through matrix, and E times Z and F times Z represent the corresponding influence of external disturbances. Initial conditions are given here at the point t0. The domains of stability of linear fractional order system models, they deviate from the classical characteristics of integer order representations. In cases in which the fractional order is taken here from this open interval from 0 to 1, like we have for our battery systems, the stability domain extends into the complex right half plane that you can see here on this left half of this figure. And this part will also be relevant for further stability investigations when we want to design state observers. In addition, we have to consider that observability and controllability of fractional order system models, they can be checked by the same criteria derived by Kalman, as they also hold in full analogy for the integer order case. In addition, we can exploit duality between controller and observer design by applying those H2 and H-infinity design criteria, which can be evaluated numerically by means of linear matrix inequality techniques. However, we have to make sure that we adjust the corresponding stability domains within those LMI representations. Now let's have a look at a fractional order system model. This fractional order system model with the corresponding derivative parameter from the open interval from 0 to 1. If we want to check whether the system model is asymptotically stable and whether the corresponding H-infinity norm fulfills the inequality that it is bounded from above by a positive parameter mu, we have to try to figure out whether there exists a solution for those matrices P1 and P2, which are both Hermitian complex matrices. Those two matrices have to satisfy the property of positive definiteness, like they are shown here on the right hand side. This criterion that you had seen on the previous slide can now be extended towards a fractional order state observer design. In the state observer, we are more or less copying the deterministic part of the original state equations, and we are feeding back with the yet unknown observer gain L the deviation between the measured system outputs Ym and the corresponding output estimates y hat. We have to prove that the estimation aerodynamics that you can see here in the lower part of the slide as the difference between the green and the blue box remain asymptotically stable. For that purpose, we can employ the previous LMI condition in such a way that we try to find an observer parameterization, like you can see it here in the lower part of the slide, in such a way that X is a Hermitian positive definite matrix and mu, as before, specifies the maximum H-infinity gain here of this expression. However, this classical observer does not directly allow for taking into account worst-case influence of uncertainty in the corresponding measured system output, and it also does not allow for directly accounting for bounded uncertainty in the system matrices A and B. For that purpose, we can try to employ an interval observer with a positive aerodynamics. This positive aerodynamics can be ensured if the corresponding system matrix of the corresponding observer aerodynamics, namely the matrix A minus L times C, is an asymptotically stable matrix, which is moreover a so-called Metzler matrix. In this case, the cooperativity and for that reason also the positivity of the aerodynamics of the system model is guaranteed. If we find such a solution, we can independently evaluate the trajectories for the lower state bounds as well as for the upper state bounds, and the same also for the corresponding system output vector y underlined and y overlined. Those corresponding bounding systems, x underlined and x overlined, as well as the corresponding expressions here for the system output, they have to be found in such a way that starting from an initial domain that is bounded by corresponding interval bounds, the true system state is always guaranteed to be inside the computed intervals. For that purpose, we have to solve the matrix inequality that you can see on the slide. Here we have to restrict ourselves to solutions that guarantee the Metzler property of the corresponding dynamics matrix of the aerodynamics of our interval observer. This can be achieved by introducing a sufficiently large parameter value kappa, and if we found such a parameter value kappa in addition with a matrix Z that is positive definite, we can further on compute the corresponding interval observer gain L. Here we have restricted ourselves to a purely diagonal matrix Z in order to be able to avoid bilinear couplings between multiple unknown matrices. As I already mentioned, the cooperativity of the aerodynamics is ensured if A minus LC is a Metzler matrix, which can be verified by element-wise checking the corresponding inequality in the red box. Now, the structural restriction of the matrix Z to a purely diagonal matrix introduces also some specific degree of conservativeness. This conservativeness could be reduced, for example, by removing the structural restriction and solving the corresponding design criteria in an iterative fashion, as you can see here in this reference. Coming back to our application scenario, namely the state of charge estimation for a battery system, we have to derive the corresponding quasi-linear state space representation where A, B, and in our case especially the output matrix C and the feed-through term turn into state-dependent entries. Those state dependencies are now over-approximated by means of a polytopic uncertainty representation for which the details can be found in the proceedings paper. If we have derived the corresponding state-dependent matrices C and D with their corresponding interval bounds, we will be able to design a robustly stabilizing observer with point-valued characteristics as well as a corresponding interval observer. Now we come to the corresponding estimation results, which we determined in a numeric fashion. Here on the left-hand side you see again the battery model for which we had derived the corresponding system matrices on the previous slide. For the sake of simplicity, we had assumed that R0 and R are constant state-independent parameters, and the nonlinearity, in our case the state dependency, only lies in the expression for the open circuit voltage, which introduces interval uncertainty in the output equation. For all simulations that you will see on the following, we take into account this piecewise defined terminal current as the corresponding control input of our battery. The corresponding measured system output is given here in the black curve, and as you can see here on the slide, although we had uncertainty in the initial conditions of our system output, our state observer with point-valued characteristic was able to trace the corresponding measured system output with good accuracy. This also holds in cases in which we take into account measurement noise. In addition, you can see on this slide that the true state of charge, which serves here as a reference solution and which was not included in any way in the state observer, is being reconstructed in an accurate fashion here by means of the corresponding point-valued state observer. Now, when we come to the interval observer, we become able to account for bounded uncertainty in the measured system output, as well as for the bounded uncertainty here in the corresponding open circuit voltage. In such a way, the interval observer determines guaranteed upper and lower bounds for the corresponding terminal voltage, as well as for the reconstructed internal system state, in our case, the state of charge. It can be shown also numerically that the estimation aerodynamics are strictly positive, as you can see it here on the right-hand side. Now coming to conclusions and an outlook on future work. What you had seen in this presentation is a state observer designed for fractional order linear system models, which can be extended easily towards the case of quasi-linear state space representations with corresponding bounded parameter uncertainty. In such a way, we can turn a point-valued observer design into an interval observer design with positive aerodynamics. Currently, we had enforced the cooperativity of the aerodynamics by a structural restriction of the observer gain matrix. In future work, we can employ some similarity transformations in order to further optimize the aerodynamics without any structural restriction on the gain matrix, and this optimization of the gain matrix will be followed by an evaluation of the state observer in a coordinate frame in which cooperativity is ensured. Finally, also iterative solution procedures which employ Mittag-Leffler type state enclosures can be used for more general fractional order system models. Before I thank you for your attention, let's have a look at a list of related publications. First of all, you will see here in the first two references listed on the slide the similarity transformation approaches that I had mentioned in the outlook of this talk. Finally, the last two references, they focus on a verified interval-based verification technique that employs Mittag-Leffler type state enclosures for uncertain fractional order system models. Thanks a lot for your attention.